Hi everybody. In a previous video we looked at the derivatives of the inverse trigonometric functions. Now remember, every time you learn how to differentiate a function, you then also learn how to find the antiderivative of a new class of functions as well, because the antiderivative just goes backwards. So in this lesson we're going to take a look at integrals involving inverse trigonometric functions. So remember, in our previous video we found out that the derivative of the arc sine was 1 over the square root of 1 minus x squared. So because of this result right here, we then have that we have this result. So the antiderivative of 1 over the square root of 1 minus x squared dx is the arc sine of x plus c. Just notice I use this notation to indicate the inverse sine function. Remember, this is not 1 over sine, it means the arc sine. Now because of this result right here, we can actually generalize it a little bit like what we have down here. So notice we can replace the number 1 here with a general value a squared. And so the antiderivative of 1 over the square root a squared minus x squared dx is the arc sine of x over a plus c. So this is merely a generalization of this result right here, where we just replace this number 1 with a number, we called it a squared. Now also notice that when we write it like this, we want the a here to be a positive real number. Correspondingly, we also found out that the derivative of the arc secant was 1 over absolute value x times the square root of x squared minus 1. So then we have this formula right here. The antiderivative of 1 over x times the square root of x squared minus a squared dx is 1 over a arc secant absolute value x over a. Notice here the absolute value here. We have an absolute value right here, but we do not have one here inside the integrand, but we do have an absolute value right here. So just take note of where the absolute values are placed for this particular formula. Also remember, the derivative of the arctangent was 1 over 1 plus x squared. So then we have this formula here. The antiderivative of 1 over a squared plus x squared is 1 over a arctan x over a plus c. Once again, notice how the 1 here, we replaced it with the general a squared right here. Now let's take a look at the proof of one of these formulas, and then we'll look at a few examples. So let's take a look at the proof of number 3 here. So because of this result right here that we discovered previously, we have that so we know that the antiderivative of this function is the arctan of x plus c. So now we want to prove this result right here. So proof of the third result. So if we start with this quantity, let's do a little bit of manipulation here. So I'm going to pull out an a squared from the denominator and write this as follows. I just want to turn it into something that looks like this. So we're going to do a little manipulation here. So all I did is factor away an a squared from both of these terms right here. Just pulled an a squared away, and we have this. Notice if I multiplied the a squared back inside, we would recover this again. So that's all I did. Now I'm going to move that a squared outside the integral, and we get and now I'm going to use a substitution. let's let u equal this term right here, the x over a. So then du will be dx over a, and moving the a over here, we then get that. There we go. Now let's do all of our substitutions here. So we see that this piece right here, the x over a, that will become a u. The dx, that will become a du. And what we get is and canceling these a's here, and now this piece right here is going to be the arctangent of u, using this result up here. Right? This looks just like this with a u in place of the x's. So this entire term here will then become and then putting x over a back in place of the u, we get and that's exactly what we wanted to prove right here. So we obtained this part right here now. Once again, notice that this is just the alternate notation for the arctangent. So this is the same as and there we go. Now let's take a look at a few examples. So for this example, we want to evaluate the definite integral from 0 to 1 of 1 over 1 plus x squared. So we have to find the antiderivative for this function first. Well, let's look back at our formula up here. Notice we have this rule right here. So in this case, the a squared is just 1, in which case a is just 1. And so following this rule right here then, the antiderivative of 1 over 1 plus x squared, well, that's just going to be our arctangent. So this equals the arctan of x evaluated from 0 to 1. And evaluating this, we get now the arctangent of 1, that's just pi over 4. And the arctangent of 0, that's just 0. And we get pi over 4. So once again, when you're evaluating these, you need to think of the arctangent of 1 as being an angle theta, in which the tangent of theta should give you back 1, right? Because the tangent of the arctangent will give you back 1, just like f of f inverse of 1 gives you back 1. And so what angle has a tangent of 1? Well, that's pi over 4. And you can also look at the unit circle diagram to determine that, or just, you can also evaluate the arctangent of 1 on your calculator. You can do this on your calculator, and you can do this as well, and you'll see that you get this. Now let's do this one down here. So we want to evaluate this definite integral. So we need to find out what is an antiderivative for this function right here. Well, notice that that matches up with this form right here, where once again the a squared is 1. And so a is just 1. And so this quantity will equal, that is our antiderivative for this quantity right here for this function. And then we just evaluate that from, and so that evaluates to And there we go. Now if you want to evaluate this, most calculators don't have an inverse secant button, but you can use the fact that this is equal to Alright, and calculators do have an arc cosine button on them. The rule that I used here, remember, is this one. This was in a previous video. Alright, that's the rule that I used here, so just flip the root 2 and 2 over root 3. Now notice that the 1 over root 2, if you try to match this up with the unit circle diagram, this is the same as root 2 divided by 2. Now the arc cosine of root 2 over 2, that's pi over 4. And the arc cosine of root 3 over 2, that's pi over 6. And so we get for our answer here just finding a common denominator. This is going to be 3 pi over 12 minus 2 pi over 12. And so we get our answer pi over 12. And so there is our answer for this problem right here. And notice once again, you could evaluate the arc cosine on your calculator, or you can use the unit circle diagram. Now let's take a look at these examples where we're evaluating indefinite integrals. So the first one here, we want to find the antiderivative for 1 over 3 plus x squared. So we look at our table up here, and it looks like it's a best match for this formula right here, where the a squared is 3. So in this case, our a squared is 3, matching these up, in which case a is the square root of 3. And so all we have to do is follow the formula right here now. And so this is going to be and there you go. That's all we had to do for that one. Just match up the 3 with the a squared term. Let's take a look at this one. So looking back at our table, it looks like this one is a best match for the arc secant formula right here. Okay, so it looks like I might try to match the a squared with the 4, but you notice the x squared right here, I have a 9x squared here instead of just an x squared, so we have to somehow get rid of that 9. Well, what we're going to do is factor that 9 away from these two terms and try to move it outside the integral here. So let's write this as follows. Alright, so you see I just factored a 9 away from the x squared plus 4 term, and we get this. Notice if I multiply the 9 back inside here, I will recover this. Now let's move the 9 outside of the square root, in which case it will become a 3, right? So this will equal So there you go, we just broke this up as a square root of 9 times the square root x squared minus 4 over 9. And of course this is 3, and we will move it out in front of the integral like this. There we go. Now this is a better match for our arc secant formula up here. So now we see that the a squared term right here matches with 4 over 9. So now we see that in which case a is just going to be 2/3, right? The square root of 4 over 9 is 2/3, and so this quantity will then equal, so using this formula right here with a equaling 2/3, we're going to get now 1 over 2/3, that's going to be 3/2, right? So this is going to be there we go. Once again, this term right here is 1 over a, and then of course this simplifies to and there you go, we have our answer. So once again, for this problem, all we had to do was do a little bit of manipulation to make this look like our arc secant formula up here. Let's take a look at a few more examples. So here we want to find the indefinite integral of e to the x divided by 1 plus e to the 2x power. Now we want to match this up with one of these formulas up here. Well, I don't see any square roots in here, so it's probably going to be a best match for the arc tangent. So let's see if we can make this look like this side right here. So to do that, we're going to do a substitution. Now, before we do a substitution, let's note that this e to the 2x, that's actually equal to e to the x, the whole quantity squared, right? So now if we think of the e to the x as being a u, the bottom will become 1 plus u squared. So now it'll look more like this up here. So now let's try a substitution, u equaling e to the x, and hopefully this will work out. So if we let u be e to the x, notice that du is going to be e to the x times dx. And now let's see how all of this works. So this, let me rewrite this as follows. So there I just wrote e to the 2x as e to the x, the quantity squared, right? All you have to do is multiply the 2 against the x and you'll recover e to the 2x. So that's by rules of exponents. And now with all of our substitutions down here, what's inside the parentheses here becomes a u. E to the x times dx, that becomes our du right here. And this whole thing just becomes, and now this looks exactly like our arctangent formula with the a equaling 1. So notice that our a is 1 here. And this is just, and replacing the u. And there you go, we have our answer. Let's take a look at a few more. Now for this example, we want to find the indefinite integral of 1 over x squared minus 6x plus 11. Now, this doesn't look anything like any of these up here. Well, it looks probably the closest to the arc tangent here because I don't see any square roots in here. So if it's going to work out with any of these, it's probably going to be the arc tangent. Now what we're going to have to do with this one is we're going to have to do a little trick called completing the square that you've seen before. So let's note that we can write this as now what we're going to do is complete the square on this, and then you'll see how we can turn this into something that looks like a squared plus x squared with a substitution. So if we try to complete the square on this, now remember the way we complete the square is we take the b term right here, b is -6, and so we take -6 over 2 and we square it. And so this is going to obviously be negative 3 squared, or 9. And so what we end up with here is, now we're going to take this, add it in, and subtract it back out. So we're going to write this as, so you notice the 9's cancel, so we haven't changed anything. Now what this is going to become right here, this always becomes x plus b over 2 squared. Now in this case, the b over 2 is negative 3. So this is going to become, and negative 9 plus 11, that's just 2. Okay, so you see how completing the square works there. So this integral I can then write as, okay, now we see how it's looking a little more like the arctangent. Now let's do a substitution here. Let's let u equal x minus 3. Then du is just dx, and this becomes now we see that this matches up with our arctangent formula, where the a squared is the 2 term right here. So a squared is 2, and so a is the square root of 2. And so this is going to be and then putting in x minus 3 back in place of the u, we get our final answer. And there we go. So that is our antiderivative for 1 over x squared minus 6x plus 11. So once again, notice that we had to complete the square on this one to turn it into x minus 3 squared plus 2. So this matches up with our formula better, and then we just did a substitution to make it look exactly like our formula up here, where we let u equal x minus 3. Let's take a look at this one. Now here we want to find the antiderivative of x minus 3 divided by the square root of 2 minus x squared. Now let's see which formula up here best matches this, just to get an idea of which one we're going to deal with. Well, I see a square root here, so it's probably going to be an arc sine or an arc secant. I also notice that we have a negative x squared here. So if I look at the arc sine, I have a negative x squared. The arc secant has a positive x squared. So this one's probably going to involve the arc sine. So once again, we're going to try to complete the square on the 2x minus x squared term to make it look like a squared minus x squared. So let's do that up here. So if we start with, now to complete the square, it's usually easiest if we have a positive 1 in front of the x squared. So let's factor out a negative 1 from this and write it like this. Now it's easy to complete the square on this. So the b in this case is going to be negative 2. And so what we want to do is look at negative 2 over 2 squared, which is 1, of course. So we add that in and subtract it back out. Now this piece right here will become x plus b over 2, or you can easily see that that factors as x minus 1 squared. So this is equal to, and then taking the negative 1 back inside, we get, and there you go. So now we have this. It does look like the form a squared minus x squared now, with x minus 1 playing the role of this x right here. So we're going to do a substitution with u equaling x minus 1 it looks like. So now we've written this as follows. So this term right here, we've now determined that we can write that as and now we're going to do a substitution. Let's let u equal x minus 1. Of course, then du equals dx. So this will become u, but the question is, what does x minus 3 become? You know, u is x minus 1, it's not x minus 3. Well, if we do this little trick, let's let x minus 3 equal x minus 1 minus 2, right? Or you could also solve this equation right here and say that x equals u plus 1, and then put u plus 1 in place of this x here. Either way works. So we see that this integral then becomes, so x minus 3 is going to be u minus 2. And there we go. Now it's looking more like an arc secant, but we have a u minus 2 in the top. So what are we going to do with that? Well, let's split this fraction apart as follows. Let's write this as so there you go. I just split the fraction apart as u over the square root minus 2 over the square root. This piece right here is very easy. That's an arc sine, right? It's an arc sine. So this piece right here, that's just going to be the arc sine of u. Notice that the a is 1 in this case. And then we can just substitute x minus 1 back in place of that u. So this one is no problem. Now this one right here is a little trickier. What this one would require, let me give myself a little room up here to explain it. What this one would require would be another substitution like v equals 1 minus u squared, in which case we would get that. So we see that this will work out, but let's try to do this one in our heads without going through the whole substitution process, right? So I forgot my du right here. There should be a du right there. So the u du is going to become some multiple of dv. So we can see that this will work out. Now, if we try to do it in our heads, so what this would end up being is something like an integral of v to the negative 1/2 power dv, and the antiderivative of this is some multiple of v to the positive 1/2 power, right? So now if we look at this, this term is going to become 1 minus u squared to the positive 1/2. Now think about this, we're going to have to multiply it by some constant out front here. If I were to differentiate this, the 1/2 would drop down, so I would have to cancel it with a 2, right? Because I don't have a 2 in here. And then we subtract 1 from the exponent here, and we'll get negative 1/2, which corresponds to the 1 over square root 1 minus u squared. So we see that's what we're getting when we subtract 1 from this exponent, when we differentiate this. But then what I would need to do is multiply by the derivative of the inside. Now the derivative of the inside is negative 2u, but we only want u. So I'm going to also have to multiply this by negative 1/2 to cancel this negative 2. And there we go. This is the full antiderivative for this up here. Notice once again, if we differentiate this, drop the 1/2 down, it cancels with this 2. Subtract 1 from the exponent, we get our 1 over square root 1 minus u squared. When we multiply by the derivative of the inside, we get negative 2u. The negative 2 will cancel with this negative 1/2 and just leave a u right here. So then this piece right here we see becomes, if we cancel these 2's, negative 1 minus u squared to the 1/2 power. So let me just clean that up a little bit and write this as and there we go. This is the antiderivative for this integral right here. And then this one over here we've already determined is, and now we just have to put our x's back in place of the u. And we have our final answer right here. And there we go. And if you wanted, you could FOIL out the x minus 1 squared and simplify what's in here a bit. Of course, all of this will just simplify as 2x minus x squared. It will just simplify to this right here. If you wanted to FOIL out the x minus 1 squared, the 1 will cancel, and you'll end up with this again. And so there we go. That's our answer. And that concludes our video on integrals involving inverse trigonometric functions.